It's a famous theorem called Rolle's theorem. Rolle's theorem essentially says the following thing. I just draw the picture from this, the statement will be very clear. I take a point A, I take a point B. Suppose I have given a function f defined on closed interval AB to R. Assume that f is differentiable on the open interval AB. Also assume that f of A is equal to f of B. So if I try to draw the graph of the function, at the point A the value of the function fa, it has the same height as fb, then the curve of the function has to look something like this maybe, if I can draw the graph of the function. From the picture you can see that at this point, at this topmost point, the tangent is parallel to the x-axis. At this point also the tangent is parallel to the x-axis. I know what it means. The tangent being parallel to the x-axis can be expressed by saying that the derivative of the function at that point is 0. So based on this picture, I will like to conclude then there exists at least one C in the open interval AB such that f prime at C is 0. Because you see why I said at least, it could have been at most also. For example, the graph of the function could have been looked like this. I take A here. Let us say the graph of the function looks exactly like this. Then it is only the topmost point where the derivative is 0. Okay? Now the beauty of Rolle's theorem is that to prove this theorem, which we know has to be true if I can draw the curve of the function the way I look like, but the graph of the function cannot always be drawn, as we have seen. So analytically one has to prove it. But for our intuition, these pictures are quite alright. It tells us that it has to happen. So let us see why it should happen. The proof is very simple. It just uses the previous observation which we have done, and we will use some property of the function, which let me put in the condition that let us say the function f from AB to R is continuous and it is differentiable in the open interval AB, and at the end points the function takes the same values. Now since f is continuous on AB, on the closed interval AB, by a property of continuous functions on closed intervals, I know there exist 2 points x0 and y0 in the closed interval AB, such that f of x0 is the maximum of all the fx's x in AB, and f of y0 is the minimum of all the fx's where x in AB. Now the possibility is that x0 and y0 are endpoints. Let us say x0 equals to A, y0 equals to B. If that is the case, since fa equals to fb, this implies that fx0 equals to f of y0. That is, the function has same maximum as well as the minimum. What does this mean? This implies that f is a constant function. That is, fx must be equals to c for all x in AB. And then it is very easy to check what is the derivative of this function. Well, we just write down the definition, limit h going to 0, f of x plus h minus fx divided by h, that is limit h going to 0, c minus c by h, which is 0. So Rolle's theorem is proved in this case. Now another case is x naught equals to b and y naught equals to a. But then this is same again. Maximum is same as minimum, implies the function is constant. Now the next thing is, suppose that is not the case. That is, either x naught or y naught is not an endpoint. So let's assume x naught belongs to the open interval AB. Notice that x naught was a maximum of the function. This certainly implies that x naught is a local maximum, and I also know f is differentiable at x naught, that is f prime at x naught exists. This implies by the previous result that f prime at x naught is 0. Similarly, if y naught belongs to AB, again by the previous theorem, f prime at y naught is also 0. So that is the proof of the result. But notice here, the most fundamental fact what I am using here is that since f is a continuous function on the closed interval, it must attain its bounds. That is, there exists a maximum of the function and a minimum of the function in the closed interval. If it happens that these two maximums and minimums are endpoints, then using the condition that f is same on the endpoints, that it takes the same values on the endpoints, we get that the function is constant, and hence the derivative is 0. Then the next case is that this maximum or the minimum lies in the open interval AB, and in that case we use the previous theorem which tells us that the derivative is 0. That is the proof of Rolle's theorem. Now let us look at some more generalizations of Rolle's theorem. The first one is the well-known mean value theorem. Look at the situation of Rolle's theorem again. I draw the picture again here, that this is A, this is B. I know the heights are same at A and B. The graph of the function looks something like this. Then there are points where the tangent is parallel to the x-axis. Now it could have happened this way also. I draw another picture, that suppose this fa equals to fb condition is dropped. That is, the height of the function here is this, height at b is something like this. So height at b is certainly more than height at a. Okay, and the graph of the function looks like this. Then what I do is I look at this line joining these 2 points. From the picture I can see what is happening is that there are points, for example, if I look at the tangent here or I look at the tangent here, they are parallel to the line joining these 2 points. Okay. Now how do I explain this geometrically in terms of the derivative? That is what mean value theorem is all about. So let's notice certain things. I want to see that the tangent is parallel to the line joining these 2 points. That means these 2 lines must have same slope. So let us draw the picture again and we will try to calculate things here. That I have the axis here. This is the point A. This is the point B. My function has 2 different heights. One is here, other is, let us say, here. My function looks like this. What are the points? Well, the points are B, FB, and here the points are A, FA. Now, I can draw the line joining AFA and BFB. This is the line. Then I can draw the tangent line also. Let us say at this point. This is the tangent line. Now, what is the slope of the line joining AFA and BFB? Well, I can actually write down the equation of this line. That is what I am going to do now. So, the equation of the line is this is the equation of the line joining the points AFA and BFB. So, the slope of the line anyway is FB minus FA by B minus A. I want to say that there exists a point where the tangent is parallel to the line joining AFA and BFB. That would mean that the tangent has the same slope as the line joining AFA and BFB. That means there should be a point where f prime of that point is same as the slope of the line. So, the precise statement of the mean value theorem goes as follows. Let f from the closed interval AB to R be continuous and differentiable on the open interval AB. Then there exists at least one C in the open interval AB such that FB minus FA by B minus A is equals to F prime C. Okay. How do you go about proving it? If you notice the previous thing carefully, that we are actually dealing with 2 functions. One function is certainly the given function fx. Another function is the line joining AFA and BFB. So, I will again write down the equation. Equation of the line joining AFA and BFB is y minus fa equal to fb minus fa by b minus a into x minus a. That is y equals to fa plus fb minus fa divided by b minus a into x minus a. Now this is another function. I can actually call it gx. What I want to do is I just want to compare this function with the given function fx. That is, I define a new function hx equals to fx minus gx. That is fx minus fa plus fb minus fa by b minus a into x minus a. Notice that h is a differentiable function on AB, the open interval AB, and continuous in closed interval AB. This is simply because h is actually given in terms of f and some other constants and the function x. All these functions has the property that they are differentiable in the open interval AB and continuous in the closed interval AB. So h also has the same property. Now notice what is HA. Now since h is a differentiable function, what we will try to do is we will try to see whether it satisfies the conditions of Rolle's theorem. That means we will try to evaluate first what is h at the endpoints. So let us first calculate h of a. That by definition is f of a minus f of a plus fb minus fa by b minus a into a minus a, which anyway is 0. So what I get is fa minus fa, that is 0. Now I look at what is h of b. That again by definition is fb minus fa plus fb minus fa by b minus a into b minus a, which is fb minus fa plus fb minus fa, which is 0. That is, h is a function which is differentiable interval AB, continuous in the closed interval AB, and at the end points it takes the value 0. That means by Rolle's theorem that there must exist a point C where the derivative of the function h vanishes. So this implies there exists a point C in the open interval AB such that h prime at C is 0. But now I can try to calculate what is h prime at C, because I know the precise description of h. So let us try to calculate that. So our definition of h is given as this: hx equals to fx minus gx, which is fx minus this quantity. So if I look at what is h prime at C, which I know is equal to 0, that would give me that this is equals to f prime C minus fa is a constant, so derivative is 0. Then what I get is fb minus fa by b minus a. This is equal to 0. This in turn implies that f prime C equals to Fb minus Fa by B minus A. Now I said that this is a generalization of Rolle's theorem. It is actually in the following sense. If Fa is equals to Fb, then it follows from mean value theorem, which I will denote by MVT, that f prime c equals to Fb minus Fa by B minus A is equal to 0, which is Rolle's theorem. So this way mean value theorem actually generalizes Rolle's theorem, that if you put the condition Fa equals to Fb in the mean value theorem, then Rolle's theorem follows. At the same time, we should not forget that while proving the mean value theorem, the most fundamental thing is actually the Rolle's theorem. What we have done is we have constructed certain functions out of the given f and have applied Rolle's theorem to conclude mean value theorem. Next we go to some more general form of mean value theorem called Cauchy's theorem, Cauchy's mean value theorem. Now we come to the mean value theorem due to Cauchy. It is called Cauchy's mean value theorem. In short, I will mention it as CMVT. It says the following, that suppose I have a function f and a function g which are continuous on closed interval AB and differentiable on the open interval AB. If g prime x is non-zero for all x in the open interval AB, then Cauchy's mean value theorem says that there exists a C in the open interval AB such that Fb minus Fa by Gb minus Ga equals to f prime c divided by g prime c. Notice here the c in the numerator and denominator are same. If I could have allowed different c's, then it would straightaway follow from the usual mean value theorem. The beauty of Cauchy's mean value theorem is you get the same c in the numerator and the denominator. Now the first question is why Gb is not equals to Ga, that is why the left hand side makes sense. So I will just note it here, Gb is not equals to Ga as g prime x is not equal to 0 for all x in the open interval AB. How does this follow? Because if Gb is equals to Ga, then by Rolle's theorem there will exist an x in the open interval AB such that g prime x is 0. But g prime is always non-zero, that is given. That means Gb cannot be equals to Ga. And now I can remark that if I take g to be the particular function, if gx is equals to x, then usual mean value theorem follows from Cauchy's mean value theorem, which is obvious because just in the expression if you assume gx equals to x, then gb minus ga turns out to be b minus a, and in that case g prime c is anyway 1 because gx equals to x has the derivative 1 everywhere. Now to prove this, I just note that what I have to prove is to prove that fb minus fa into g prime c equals to f prime c into gb minus ga. This is what I need to prove. So for that, I just look at the function hx equals to gx into fb minus fa minus fx into gb minus ga. And then let's just hope that perhaps H satisfies the conditions of Rolle's theorem. Let us see, G and F both are differentiable functions on the closed interval AB. Both are continuous functions on the closed interval AB. Then suddenly H is a continuous function on the closed interval AB. Moreover, F and G both are differentiable functions on the open interval AB. So H is also a differentiable function on the open interval AB. Now I just want to check what is H at the endpoints. Well, what is HA? So H of A then is GA into FB minus FA minus FA into GB minus GA. If I expand this, what I'd say is that FA and GA cancel each other, so we just open it up and check what happens. It is GA FB minus GA FA minus FA GB plus FA GA. Then FA GA cancels each other. What I get is GA FB minus FA GB. Now let's look at what is H of B. That by definition is GB into FB minus FA minus FB into GB minus GA. I again open it up. It is GBFB minus GBFA minus FBGB plus FBGA. Here I see what get cancels is it is FBGB cancels each other. What I get is FBGA minus GBFA, which is same as HA. This implies by Rolle's theorem there exists C in the open interval AB such that H prime C equals to 0. But from the definition of H, again I can calculate the derivative. This implies G prime C into FB minus FA minus F prime C into GB minus GA equal to 0. This then implies that G prime C into FB minus FA equals to F prime C into GB minus GA. This is precisely what we wanted to prove. Next, let us go to the applications of all these tools which we have developed so far. So we start with one obvious thing. Suppose let f be the constant function. That is, f of x equals to c for all x in, let us say, open interval a b. This would certainly imply that f prime at x is equals to 0 for all x in the open interval a b. This we have observed from the definition of the derivative. Question is the converse. So the question is, if f prime x is 0 for all x in open interval a b, is it true that f is a constant function in the open interval a b? This is really the converse, that if a function is constant, then its derivative is 0. Question is, if its derivative is 0 at all points in an interval, does that mean the function is constant in that interval? Notice that the question involved the whole interval. It is not about points. A non-constant function might have a derivative which vanishes at a point. That is not the point. The point is, if you have a function whose derivatives vanish in an interval, then can you say that the function is constant? It turns out to be very simple by mean value theorem. That suppose not, suppose the answer is no. Suppose x1 not equal to x2 belongs to the open interval a b, and fx1 is not equal to fx2. Then I know by mean value theorem there exists C such that fx1 minus fx2 divided by x1 minus x2 equals to f prime c. Now, since fx1 is not equals to fx2, the left hand side has to be non-zero because x1 is not equals to x2. This would imply that f prime c is not equals to 0. But this is a contradiction because I said that f prime vanishes everywhere. This implies the function must be constant function. That is, take any two x1 and x2, fx1 has to be equals to fx2. That is what we mean by saying that f is a constant function. But notice here that we need the condition that the derivative of the function vanishes everywhere in the interval. Why so? Because if you look at the c which appearing in the mean value theorem, this c actually depends on x1 and x2. I can actually say c, it is a function of x1 and x2. Once you change x1 and x2, this c will also change. So unless you know that the derivative vanishes everywhere, you cannot show that fx1 equals to fx2 for all x1 and x2. Anyway, using mean value theorem, now we have seen that if a function has the 0 derivative everywhere, then the function has to be a constant function. Now the next application we are going to do is a famous technique of applying limits called the L'Hopital rule. The next application is the famous L'Hopital rule. So our situation is something like this, that I have functions f, g defined on open interval ab to r. Let us say x naught is a point in ab and f of x naught equals to g of x naught, let us say is equals to 0. Assume that g of x is not equals to 0 if x is not equals to x naught. Then I can be interested in finding the limit x going to x naught fx by gx. You can see there is an obvious problem because I cannot just write fx naught by gx naught as the limit, because f of x naught is 0, g of x naught is also 0. So it is the famous 0 by 0 case. Now if I assume that f and g both are differentiable functions, assume that f and g are differentiable, then the L'Hopital rule says that limit x going to x naught fx by gx is same as limit x going to x naught f prime x naught by g prime x naught, provided the right hand side exists. Okay. As quick examples we can look at, let us say fx equals to sin x, x in minus 1 1, gx equals to x, x in minus 1 1, and I am interested in finding limit x going to 0 sin x by x. Notice that g satisfies the condition of the L'Hopital rule that g is non-zero at any other points except 0. So if I can apply L'Hopital rule, it would say that this limit is same as limit x going to 0 cosine of x divided by 1, which turns out to be equals to then 1. It becomes that easy. Now let's go to the proof of the result. What we will show is, we will prove that limit if limit x going to x naught plus f prime x by g prime x is equals to L, then limit x going to x naught plus fx by gx is also equals to L. So we start with fx by gx. I write it in the form fx minus fx naught divided by gx minus gx naught. And since I am interested in the limit x going to x naught plus, I will take x to be strictly bigger than x naught. This I can do as fx naught equal to 0, which is equals to gx naught. Now I am in a position to apply Cauchy's mean value theorem, because in a neighborhood of x naught, f and g both are differentiable functions, so anyway they are continuous. It implies then there exists a C such that this is equals to f prime C divided by g prime C, where C lies between x naught and x. Now I want to take the limit as x going to x naught from the right hand side. Notice that C is sandwiched between x and x naught. I can actually write C suffix x, because C depends on x. This would then imply that limit x going to x naught plus fx by gx equals to limit C going to x naught plus f prime C divided by g prime C. This actually follows from the sandwich theorem, that since x converges to x naught and C lies between x naught and x, it has to converge to x naught. But now the right hand side is L, that is my assumption. So is the left hand side. Similarly, applying the same technique of applying Cauchy's mean value theorem, we can prove limit x going to x naught minus fx by gx, that is also equals to limit x going to x naught minus f prime x by g prime x. I will just make one remark here which becomes useful, that if limit x going to x naught f prime x by g prime x is infinity, then so is limit x going to x naught fx by gx, because our proof does not actually depend on the value of L, which is the limit. As an example, let us again look at the following limit. Now I will just like to mention that if the situation is something like this, that limit x going to x naught fx is equals to infinity, which is same as limit x going to x naught gx, and gx is not equal to 0 for all x not equals to x naught, and f and g are differentiable, then limit x going to x naught fx by gx is limit x going to x naught f prime x by g prime x, provided the right hand side exists. This is the famous infinity by infinity form. As an application of this, we can look at the following example. Let us try to calculate the limit x going to 0 x log x, which I write as limit x going to 0 log x by 1 by x. If you like, I might start with minus here. I will put minus here. Now I define fx equals to log x with a minus sign, gx equals to 1 by x. Then f and g satisfy all the possible criteria here. By L'Hopital rule, this implies that limit x going to 0 minus x log x is equals to limit x going to 0. Now the derivatives come, that is minus 1 by x divided by minus 1 by x square, that is limit x going to 0 x, which is equals to 0. This implies limit x going to 0 x log x is also equals to 0. So notice that here in this setup, to apply L'Hopital rule, we actually needed the infinity by infinity form of the L'Hopital rule. These are the famous indeterminate forms. One is the 0 by 0. The example we have seen is sin x by x. Other is infinity by infinity. Here the example we have is x log x. Now let us start with the geometric interpretation of the Cauchy's mean value theorem. I have given two functions f and g. I look at a curve defined as xt equals to ft and yt equals to gt. So the points on the curve are given by ft, gt. As an example, I can look at ft equals to sin t and gt equals to cos t. Okay. If t varies from 0 to pi by 2, I will get something like this as my curve. Now, given this situation, what does Cauchy's mean value theorem say? So let us say this is the curve where the points are given as ft, gt. Both are differentiable functions. Then it says there exists a point C where at C the slope of the tangent line which is given by f prime c divided by g prime c must be equal to the slope of the endpoints. So the endpoints we know are FAGA and FBGB. These are the endpoints of the curve. Then the slope of the tangent line, if we look at, that is FB minus FA by GB minus GA. Cauchy's mean value theorem says that this slope is same as the slope f prime c by g prime c. At the point C, the slope of the tangent line is given by g prime c divided by f prime c. On the other hand, if I look at the endpoints which are given by FAGA and FBGB, then the slope is given by GB minus GA by FB minus FA. And then Cauchy's mean value theorem says that this slope is actually same as pretty similar to the usual mean value theorem.